Hi everyone, my name is Ihor. I'm co-founder and machine learning lead at Knowledge Gateway Engineering. I'm presenting a talk on comparative analysis of information theory-based statistical methods and transformer-based machine learning techniques for scientific literature classification. I will start with the importance of text mining and classification in science, followed by a particular challenge description and explanation of two methods we use to solve the classification problem. Then we will dive deeper into analysis of statistical method and its comparison to the transformer-based approaches. So let's start. More and more papers are produced yearly, and it becomes difficult to process this corpora manually to extract relevant information. Drug-induced liver injury is a clinically significant condition and one reason for drug registration failures. For now, the scientific literature is the primary source of information for DILI, according to FDA. Therefore, it will be very beneficial to automate the information extraction process from the documents. This could have saved hundreds of working hours and speed up the drug discovery process. Thus, we took part in the CAMDA challenge that provides biomedical publication created by FDA experts on DILI to build a classification tool. CAMDA committee and FDA provided a training dataset with 14,000 DILI-related papers equally divided into positive and negative examples. It will also given test and validation datasets that are unbalanced into different degrees, include more and more true negatives to reflect the difficulty of the real-world task. Moreover, to test the overfitting of models, the first validation dataset consists of 14,000 expert summaries of the research instead of extracted articles abstracts. On the figure, you can see the distribution of the most frequent words in each dataset. But as one can assume, the classes DILI and not DILI are unbalanced in the real world. By unbalanced in this case, I mean that the number of concepts that determine the not DILI class is much larger than the number of concepts that define the DILI class. This can be seen visually on the left panel of the figure. For better analysis of our methods, we tested them on other datasets, such as IMDb reviews dataset consisting of 25,000 positive and the same amount of negative reviews. We use this dataset to test how our method performs on balanced dataset by the number of concepts that determine the class. Comparing the distribution of most frequent words in categories could help understand this better. From the figure, you can see the distribution for the two classes are somewhat different in the DILI dataset, and for the IMDb dataset, they are nearly the same. Our statistical information theory-based method consists of calculating the PMI, point-wise mutual information, and TF-IDF, term frequency, inverse document frequency. From equation 1, we can see that the PMI is meant to account for words that are very frequent inside class examples. The more frequent word inside the class and the less frequent the same word outside the class, the greater PMI we will have for the word in that class. In equation 2, we just normalize PMI to get values from -1 to 1, meaning that if class and word occur together only, normalized PMI would equal 1. To calculate TF-IDF, we have to multiply together term frequency and inverse document frequency. Term frequency is the number of times a given word occurs in the text. In contrast, an inverse document frequency is the inverse of the number of documents in which a word occurs divided by the total number of documents. Intuitively, PMI accounts for the importance of the word in the given class if the word is frequent, and TF-IDF mostly prefers words that are rare in the corpus, but are very frequent in some particular documents. Therefore, TF-IDF determines the importance of the word for the particular document. In order to make an inference about a new document, we divided the document into sentences, tokenize these sentences, and remove frequent English words and punctuation. Then we will calculate for each class F a sum of TF-IDF times normalized PMI for each word in the document. Then we make an inference by choosing the class based on the highest value of F. Because PMI is not directly designed for classification tasks, for the current CAMDA challenge, we decided to add additional weights trained using gradient descent. In equation 7, you can see a variant for binary classification, but it can be easily adapted for multi-class classification. This approach has a little drop in speed, but it notably improves accuracy compared with classical TITs. Let's talk about transformers. As our second approach to this problem, we use transformer-based architecture. Transformers are deep neural networks that utilize the idea of self-attention, meaning that for each token in the document, we try to understand how it depends on all other tokens. This is implemented through the idea of generating keys, queries, and values matrices for each document. By multiplying queries by keys, we select particular keys, and when we choose the keys, we multiply them by values, therefore selecting some values. All of this is done in parallel by generating different matrices that convert the input matrix to keys, queries, and values. We decided to test two types of trained models, such as Scibart and Longformer. The main difference is the number of tokens that can be used as the input to the model. 500 file tokens is the standard limit for BART models, but our dataset contains many examples from more than 500 file tokens. Also, an essential difference between these transformers is that Longformer utilizes sliding window attention, when only a limited number of token embeddings are selected for attention. Let's discuss results on initial dataset. On the initial dataset, TIS and our weighted version TISnet showed results comparable to the transformers' performance, but at the same time they work much faster than transformers. Longformer shows the best results, ability to utilize sequences longer than 500 file was beneficial for a given initial dataset, where more than 10% of abstracts has this length. The results for validation dataset are much different than on initial set due to different portions of positive examples. Longformer has the best performance of validation set 1, where we have an equal amount of negatives and positives, but it drops significantly on more unbalanced datasets such as set 2 and 3. At the same time, T significantly outperforms transformers on validation set 3 with a small portion of positives. Our weighted version TSNet demonstrates overall better performance than classical. On validation set 4, which was designed to check our fit in absolute leader, is TSNet. Longformer is more sensitive to changes in data sources. Here you can see plots that visually compare models' performance on different datasets. This plot can explain a lot of the model's performance. These models demonstrate a smoother increase of true positive rate with false positive rate compared with Longformer. Longformer has a more explosive nature. One can see from the ROC curve. It can achieve maximal performance earlier than TIS. Still, in situation with unbalanced data, we will significantly drop in precision if we want to achieve a maximal F1 score. We decided to check how the performance of TIS depends on the dictionary size. For the daily dataset, a recall is changing only slightly with the dictionary size, meaning we do not need many words to classify something as daily. This is contrary to the IMDb dataset. In the first case, we have two classes that are not balanced by the significance of words, daily and everything except daily. Some words guarantee something is daily related, but there are no words that guarantee the same for everything except daily class. From the figure, we can see that our method is very robust. Only after replacing 28% of examples with incorrect labels does the method start showing an accuracy of less than 90%. These results are quite promising, as we would like to investigate them in the future, especially if we can obtain true classes for validation datasets. So let's compare our method to transformer-based architecture. This, compared to a transformer, doesn't encode syntactic and semantic information, leading to worse performance on short documents. But our statistical method demonstrates extra low training and inference time. A more straightforward interpretation of the results makes it a good choice for first step analysis of corpus of text. And conclusions. This is an extremely fast method that accounts for the importance of the words inside the class and inside the document under consideration. Transformers are slow but could give significantly better results on short documents when compared to methods that do not account for context. We showed that in both cases, it is possible to obtain reliable results which make it possible to significantly improve the automation of daily text classification.